First of all, I know it has been a long day. Thank you so much for joining this session. It's the last session. I promise to keep you entertained with my co-speaker Suman for the next 40 minutes. So my name is Divya and I'm a specialist solutions architect for RDS Postgres. And I've been with AWS for almost 7 years now. And my primary, my day-to-day job involves helping customers working with RDS and Aurora Postgres by adopting it and also optimizing their workloads on the same. So today, I'm joined by Suman, who's just sitting right there. Maybe he'll introduce. Yeah, he'll probably introduce himself later. But so we both will be basically discussing the RAG capabilities of what is RAG with generative AI and some of the features of pgvector which you can use with RDS and Aurora Postgres. So we'll discuss some of those things and then we have a demo at the end as well. So generative AI has taken the world by storm, and I'm sure you've heard this statement many times today, right? So, but these models are trained on vast majorities of unlabeled data, right? And this data can be of different types. It could be text, it could be images, it could be videos, and much more. And instead of having one model per task, like traditional machine learning models, how does foundational models differ? So if you see on the left, I have traditional ML models where you have one model and you train it for some labeled data, and then it does some tasks, right? It could be summarization, text generation, Q&A. This is one task, one model. This is the traditional machine learning model way of doing things. But this could be tedious, right? Because if you have different use cases, you have to train different models on the labeled data to get the desired result you want. Whereas for foundational models, instead of gathering labeled data for each model and training multiple models, you just provide unlabeled data of different types. And this is not just, this is vast amounts of data I'm talking about, right? So you train it against vast amounts of unlabeled data to basically enable you to do the different tasks. And however, there are some challenges. There could be some challenges with traditional foundational models, which could be knowledge cutoff and hallucinations. I'll go to them one by one. But by knowledge cutoff, I mean, if I ask, let's take a very simple example of a chatbot. If I ask that chatbot a question of some event which very recently happened, right? For example, magnitude of a recent earthquake in Taiwan last week, it might be trained for a specific cutoff date, the model. So let's say the model is trained till December 2023. So it does not have that information. So there is a knowledge cutoff there. It does not know the answer. Or even, I actually think hallucination is even worse, because hallucinations is when a foundational model gives you back a factually incorrect information with confidence. So that is even worse, because if I don't get an answer, that's fine. But if I get something incorrect, that's worse. So that is what hallucination is, when I don't know the fact, but I am giving you the information, the incorrect information. And these are the limitations for language models today. But is there a way to fix it? So for now, let's take this example of we have a foundational model and you ask it a prompt question. Let's say, explain thermodynamics to a middle school student, right? What it would do is it would take some it is trained on some data from the web or it takes some data from the web or wherever it has information from, the data it's trained on, and give you a response. But is this response basically somehow customized to a use case? Or what if you could give it some information about your context? Like, your company stats from the last month, or any other statistics which is more contextual to your use case. What if you could do that? So that is customization, and I'm going to hand it over to Suman to explain it further.
Okay. Can you hear me? Okay. Yes? Okay. Thanks, Divya. So, hello, everyone. My name is Suman Devnath. I work with the developer relations team as a principal developer advocate for machine learning. And what we're going to talk from now onwards is how you can customize your large language model to do something meaningful for your use case. So Divya touched upon how foundational models are built and how fundamentally they are different from a traditional machine learning model. So before I go ahead, one small example that I want to give you, which will build the intuition at what we are going to talk next, is that when you think about foundational model, think about that you are training a model just to understand the language. It might be English, Spanish, or whatever it is. And after that, you are expected to do something which you can leverage from that particular model, because that model understands English or Spanish, right? So then you can ask any question. For example, if you are in, let's say, 5th grade, and if I tell you that there is a fire on the stage, so you can immediately say that this is a negative sentiment. Although, till that 5th grade, you have never learned what is negative sentiment or what is positive sentiment. But since you have an understanding of English, it was very easy for you to make that judgment that it is a sentiment analysis. I mean, it is a negative sentiment. Okay. So how we can customize our model? So the first way to customize is using fine tuning, which is similar to this. What the example I gave is that that kid is now able to identify what is a positive sentiment and negative sentiment. Now imagine that I am telling that kid hundreds of such examples where that kid just know English as of today, but you are giving him or her thousands of examples of positive sentiment and negative sentiment. And after that, you expect that kid to respond to any situation. So this is nothing but fine tuning, where you take any large language model from Anthropic, Claude, Mistral, you name it. And then what you do is you fine tune with respect to your data. And your data should be labeled. Unlike how the large language model was trained, when Divya mentioned that it takes only unlabeled data, while you're doing the fine tuning, you have to make sure that you give the trained data, labeled data. Just like in the kid's example, you are giving us a situation, and you are telling the kid that this is a positive sentiment. You're telling another situation, you're telling that this is a negative sentiment, right? So this is what labeled data is about, right? You have the data along with its label. But this is a little cumbersome because you need to have some machine learning expertise. And what essentially happens under the hood is when you provide your labeled data to the large language model, there are few weights which got changed in the last layer of that model. Okay? So this is about fine tuning. What are the other things that we can do? The other thing that you can do is you can continue the pre-training, because Anthropic, Claude, Amazon, we have trained our model, what we are calling it as a large language model or foundational model. What you can do is you take that model and continue that pre-training, but now you are doing it with your data. And the difference is, with respect to fine-tuning, is that for continuous training, you are actually using unlabeled data, just like the data that was used for pre-training. But again, this also needs a lot of resource and background around data science, and it is time cumbersome, right? And it's not always you have all of your data rightly available in the way that a model can understand. And the last is retrieval augmentation, or information retrieval. And this is where RAG comes in. So what you do is you take the model as it is, but when you ask the model, you don't ask the model the question directly. Rather, you first ask the system to get some context from your data, and then you take that context and your question, and then you ask the large language model. So the large language model knows your question, and it also knows some context. You can think of it like this. So let's say this is a library, and there is a gentleman sitting in front, and you have some question. and you just ask some question to that person, and that person goes through this library, and he picks 5 books, and he just gives you that 5 books, and he says that, okay, take these 5 books, you should have the answer in this. So these 5 books are nothing but the context, and the question you already have. So now it's your job to find the answer. And this is where RAG comes in, and we will, when we go through the demo, you will get the intuition about how these two things are connected. So today we are going to talk about this, but always remember that there are other options available. One is fine-tuning, another is continuous pre-training. Okay, so all right. So before we jump into RAG and how we can implement that, we have to first understand in what language we can talk to the large language model. So the fundamental theory here is we are talking about a language, or in this case, let's say English, but it could be any other language. And the way that computer understands is numbers, right? It's not the binary numbers. That is the it's at the very lowest ASCII level, but it's just an array of numbers. So let's say you give any sentence like, I am at AWS Dublin conference. So this this statement, you cannot throw to any large language model or to a RAG system. So you have to convert that into numbers. So what vector embeddings is basically is to find and convert this English text into an array of numbers. How many of you have heard of tokens in the context of large language model? Tokens, 5 billion, yeah? So what is that token? So token is basically, to keep it very simple, you can consider that as one word as token, but technically it's not one word. It could be a middle of the word. Like let's say going, maybe 2 tokens, go and ing, because ing is a prefix which can be, postfix which can be attached to a lot of other words. So there is no point to store going, doing, sleeping at different, in the form of different embeddings. So here, in this sentence, I am at AWS Dublin, this is converted into this array of numbers. In reality, what would happen is it will first convert that entire sentence into small tokens. So for example, I, am, at, and so on. And then each of those words will be converted into an array of numbers. So now this is the numeric representation of your data. And the better the representation is, the better model that you will get, or the better response you will get. So all the AI-based startups, Amazon and all other companies, they all are training their model to get a better representation of your text. And that's why we see that 50 billion parameters, 70 billion parameters, it's nothing but that many number of parameters are used to get your representation of your number. All right, so let's see how things work in the context of RAG. So let's say you have your data. It could be image data, text data, or a video, or anything of that sense. Right? So you don't have to think that this only works with text, although that is the most common use case. But imagine that you have an image. You break that image into pixels, let's say 512 by 512. Every pixel, you represent that in the form of array of numbers. Okay? So what you do, you take your data. So first, you have to convert that into an array of numbers, right? So we have not yet come to asking questions and all. So we are in the time where we are processing that data. So we take one of the machine learning model. We don't care what model it is. For now, let's say that we are using Bedrock, and one of the embedding model which converts that data into an array of numbers. That's all. It's the most basic thing that you have to do before you even start working with RAG. And what you do with that data, you have to store that data into some place. And what is that place? You have to pick up one of the vector stores. So we have a lot of vector stores functionality available on AWS. In this case, we are going to use Amazon Aurora, which is one of our relational database service. And Divya is going to dive deep into that in a moment. So once you have your data stored in this database, we are done with the prerequisite to get started and leverage large language model. So once you have your data into this database, now when you ask the question, do you feel that you will ask the question directly to Bedrock or any large language model? Yes, no? How many of you feel yes, you should ask the question directly? Okay. How many of you feel no is that you should not? Yes. So we should not ask the question directly to Bedrock, right? Because if you had to do that, what is the point of doing all this exercise, what we did earlier? So first thing that you will do is you are going to ask that question to Aurora or the vector store or a vector database of your choice. And you can think of it as the librarian, and it will give you some context, right? These are the 5 books in the earlier example which we took. And it will just give you some relevant data which is relevant to your question. And how it is doing that? It is doing that because you have stored the data into numbers, and we are doing a semantic search. It's not like a text-based search where you say that, okay, select all employees from this database where employee number is this. We don't do that. Here, we are doing a semantic search. That means whosoever are closed, like it's not exact, closed, just give me. Okay? So we will dive into that a little bit late when we discuss different similarity mechanisms. And now you have the questions and have the context, so you can ask Bedrock, and Bedrock will respond. Right? So this is the whole life cycle of RAG. And who will do this interaction with the database and interaction with your large language model? There are a lot of tools available, but we are using LangChain for this demo. But you can use Bedrock agents, and there are a lot of third-party tools. But LangChain is mostly common in this field. So let me give you a quick 30 seconds demo. So we have one of our employee, Ricardo. He's mostly focused on open source. He's based out of London. So he writes newsletter every week. So now what I've done is I've collected all his newsletters for last 1 year, and I created a PDF so that I can ask questions about the newsletters, because his newsletters are very, very recent and relevant. So what Divya mentioned earlier, that when you ask some question, relevant question, like what is the magnitude of earthquake in Taiwan, it was not able to answer because it's a knowledge cutoff. But here, we should be able to get that answer because that newsletters are all very relevant, and we are not going to ask questions directly to the large language model, but we will use a vector store to store the embeddings of this blogs. Okay, so here, if you see, now you get an option. Let me see if you can play this. Can you try to play this? Yeah. Can you click on play? Yeah, thank you so much. So here, you can browse and select the PDF or whatever data that you have. It could be an S3 bucket as well. You can select the large language model that you want to use to ask the question. And if you see here, we asked who are the top 10 open source contributors for that particular year, and it could able to fetch that information from the blogs that were stored in that PDF. If you ask the same question to Claude or any large language model, it will just give you a random answer. So this is the benefit. So another question that we have asked is, when is the Open Source India conference scheduled? So it is saying that the conference is scheduled in October 12th at Nimhans Convention Center in Bangalore. So these are the things that you can do when you use a RAG. So it is actually doing a semantic search on the database. So when I ask a question, that question is not going to Bedrock directly. It is going to take that contextual information from the database using the vector store, and then it is getting the answer from the large language model. Okay, can we go to the next slide, please? Can you go to the next slide? Yeah, just go to the next slide. I think it's again playing that. And all of this code, I'll share it in the GitHub repo if you want to try this out. It's a simple Streamlit application, and you can just just have a look. Okay, so now we talked about vector store as Aurora, but we do have a lot of different vector stores like OpenSearch, then Aurora, Postgres, which is the focus today. Then we also have MemoryDB for Redis, Neptune, DocumentDB, and DynamoDB. One more we have, it's Kendra, which is not a vector store, but you can also leverage Kendra for this. But I don't want to dive into all this service kind of a discussion, but I'll hand it over to Divya, where she will dive into more on Aurora and how you can leverage that. Yeah.
Can you hear me again? No, seems like not. Now, yes. Okay, so thank you, Suman, for a great insight into what RAG is. Now let's dive deep into my topic of interest, RDS and Aurora Postgres, how you can leverage an extension to basically have those generative AI capabilities, right? First of all, why Postgres? So how many of you actually use Postgres today for your workloads? Wow, okay, that's great. And how many of you use RDS or Aurora Postgres? Very good, very good. So right now, the vector capabilities, which Suman actually discussed before, is available only for RDS and Aurora Postgres for the relational side. It's not there for the MySQL bit. So we'll get into why Postgres. So Postgres is the most advanced open source relational engine. And it has an extension which is called pgvector. Now, what are extensions in Postgres? Extension is just a module or a program which can be installed into the existing Postgres source code to extend its capabilities. So because there are a few Postgres users in the audience, I'm sure you must be using, let's say, some other extensions like PostGIS for geographical storing data, or using that, or pgstat statements, or there are a lot of different extensions. And pgvector is one of them to help you with your vector search and vector storage capabilities. So it's an open, of course, you can just install it on RDS or Aurora Postgres, the extension, and you can use IVF flat or HSNW indexing techniques, and it works perfectly with these existing clients. You don't need to do much. In RDS and Aurora Postgres, it's just a command to basically create the extension, and is available for both RDS and Aurora. So this is the exact command you need to write, create extension vector. And what it basically does is it creates a new data type of type vector. And now you might ask the question, but why would we use this? Because we have had arrays and cube in Postgres for a long time now. So why should we use vectors, or why should we use this extension? So the two main reasons which come to my mind are the limitation on the number of parameters, what Suman was mentioning earlier, the number of parameters you can store for a particular vector, and the second one is the vector capabilities. So this capability of searching, the capability of being able to do these searches, right? So being able to calculate the distance between two vectors. So you have a couple of different ways how you can do that. Because what we are trying to do is, we basically have a query vector, right? So like, for example, Suman gave an example of a question you ask a kid, right? You have that query vector that, okay, what would you do if there's a fire on the stage, right? That is your query. But how close is that query to the information I have, to the vector embeddings which I have already, those numbers, right? So in order to get the answer, so the closer it is to the existing vector embeddings, that is my answer, right? So you have these different ways of calculating the distance between vectors with the pgvector extension, with the vectors you get. Sorry, can you change this? Okay, thanks. And you can use the searches as it is, but what if you need speed, right? You need it to speed it up, because think about it this way. If you are storing the vectors and they have a lot of dimensions, millions of dimensions, or the number of dimensions you can have, if you have more dimensions and you are searching against it, it can take a longer time, depending on how much data you have, right? But and that is because it does an exact search. So when you are asking, when you ask a question, it matches it exactly to what you have. But what if you could do an approximate search, but faster? So using indexes, you can do an approximate nearest neighbor search with some trade-off to the answer. So basically, you might get different answers if you're using indexes, but you basically trade off for speed, because you're doing an approximate search and not an exact search. It would be faster. And at this time, pgvector supports two types of indexes: inverted file flat and hierarchical navigable small world indexes. So let's try to understand these two index types, right? So the IVF flat indexing, what we do is you have your query vector. So let's keep that aside for a minute. But those are all the vectors on the top. So the first box which you see, that is all the vectors you have. Okay. Now, what you do as a first step is cluster the vectors into buckets, each having a centroid. And by centroid, I mean one vector which is let's say equidistant to all of them, right? So you have the centroid, and then you take your query vector and find the nearest centroid by comparing the distance to each of those centroids. So you take the query vector there and you compare it with all the centroids. And by comparing it, you understand that, okay, this vector, the query vector, is closest to this bucket. So as you see here, we are taking a bucket of vectors, and it is very clear that this is an approximate nearest neighbor search, right? The second type is a bit more complex than the first one, but I will try my best to explain it. So you have the hierarchical navigable small worlds come from navigable small worlds, which basically means you have different graphs, different layers of graphs. This is the first layer, right? This is the topmost layer where the vectors are further away from each other, right? So in this first layer, you have your query vector, just like the previous example, and you have an entry point. This entry point is defined already, right? You enter via this entry point into the graph, and you calculate the distance of this query vector to all the points here. So if you see, the query vector was closest to the second point in the first layer, right? Now we move to that point, because we know this is closest to my query vector in the first layer. Then I have the second layer, where now I calculate the distance again of the query vector with the other points, right? So now my point of interest has moved to the point below, because that is closer to my query vector. And as we go from layer to layer, these vectors are closer to each other. So now when we go to the lowest layer, we see that, okay, that red dot which you see is the closest to my query vector. So this is the result which I will return. And that's why it's hierarchical, because it has these layers and we have to calculate it this way at each layer. Now, for the next part, Suman will go over a demo for you for using this knowledge which we have explained just now about vectors, and using Aurora Postgres for resume screening. Thank you.
Thanks so much. Okay, so this is a very complex topic, to be very frank. These architectures and the algorithm that is being used for sorting. If you have worked in distributed systems or databases, you have B tree, B plus tree, if you have worked in that. So it's similar to that, but this is used in vector embeddings or vector stores. All right, so what we are going to do now is I'll quickly show you whatever we have learned so far, and we will conclude with that in next 2 minutes, is how these things work in practice. So imagine that you are a hiring manager or an HR firm, and you would like to shortlist few of the candidates for your company for a particular position. Now you got hundreds of resumes. So now you want to make your system a little bit more efficient by using RAG and vector stores to shortlist the top 2 or top 3 candidates, and you can start the interview process. So first, before I show you this, don't take this example as is. This is just to give you an intuition that what are possible, what are the things that are possible. But you can imagine the same thing in a chatbot, in any of the third-party companies that you might be using, or any of the apps that you have in your phone. In fact, with phone, I just forgot to mention, how many of you use Amazon app in your phone? Yeah. Have you ever tried that image search option when you search for a product? Have you tried that? Yes? Not many. OK. So when you go out from this room, you just open your app. Instead of you go to the search button where you type your product that you are looking for, you will see that there will be an icon where you can just click and you can use your camera to take a picture. So you take anything like your mobile phone, pen, whatever you find, just take a picture. You will find that it will search and it will give you that product. We typically use in the Western countries, you will see that people use that at Walmart or Target, because you can search and check the price and you can get the price match in the store itself. So under the hood, we are using vector search in that, when you are doing that search. Okay, just to give you that context. All right, so this is a quick demo. So what we are going to do now is we will be putting some job description, and then that job description is nothing but is our query, right? So this is our job description, and then we will also upload some resumes, and then we will try to find what Divya was mentioning, semantic search, that which are the resumes have a semantically close with respect to the job description. And after that, we will say that, okay, these are the 2 or 3 resumes. We can define how many resumes we want to shortlist. We will also use a large language model to do a summary of those shortlisted candidates, so that when your hiring manager gets that resume, he or she will also get a summary of that candidate. Okay, so that's a pipeline. So here again, this is also available in GitHub. You can try it out of your own in your account. So first, what we will do is we will go and check for one of the opening or whatever is the job description, and you can just copy that, and we are going to paste that here. So I've also put one tab so that you don't have to search for that when you're trying it. You can just click on that. You will see some job description downloaded in your browser. And then we will say that we want the top 2 resumes, and these are the resumes, sample resumes. This is also available in the GitHub so that you don't have to search for resumes or open a rack just to test this out. And then you can select the large language model of your choice, and that's it. Okay, so that's what you have to do. And now what is happening is, at this point, it is now creating the embeddings of all those resumes and your job description. And then once it is done, it is storing it in Aurora, and then using Postgres and pgvector as an extension, it is able to do a semantic search. So here, if you see, it has shortlisted 2 resumes. It's still going on. Yeah, so these are the 2 resumes which we got as a context from that semantic search, and we also got some summary. So this summary will help the hiring manager to take a quick decision before even opening the resume. And this summary is coming from the large language model directly, because you are going to, let's say, Anthropic or Claude in this case, and saying that, okay, this is the vector for a person. This is nothing but a resume for me as a human. Can you just summarize that? And it is able to summarize that person. Okay, so that's all I have for this particular demo. But I just thought to give you a run through of this architecture. Okay, so we had the job description, we had the bunch of resumes, and we also defined how many resumes we want. Now, this is if you are from the development side, I just gave few of the code snippets so that you get the intuition. So here, how we are creating this embeddings, we are using LangChain, which we have seen and earlier in the session, and we are using the pgvector class. And the way that we create is just simply pgvector from documents, and then we list all those 7 resumes. So that's all. You don't have to do anything of your own. And then you just do a semantic search in your vector store by giving the job description and the number of resumes that you want. So again, we are using the vector store object, which we created here using LangChain. And once that is done, what we want is to create a summary. And the way that we create a summary is using, again, LangChain summarize. And we can just provide the large language model, which in this case is Bedrock. If you see the Bedrock in the brackets, I have not mentioned anything. But when you look at the code, you will see that we have used Claude. So we just mentioned that Claude, model ID of the Claude in the Bedrock function call. That's it. So we can just get the summary and return that function. So the whole thing is wrapped around a Streamlit application, which you can find in this GitHub repo. And this GitHub repo also have one blog post, which I published a couple of weeks back, which goes a little deep into embeddings and how different indexing algorithms work, which Divya mentioned in his presentation, that how efficiently you can do that semantic search. So if you want to dive deep and learn that a little bit, you may like to visit that. So, but everything is there in this GitHub repo. It has this particular demo, but also there are a bunch of other demos. So if you have any questions, feel free to ask. We will be around. But thank you so much for your time. Really appreciate hanging on till the last session on the for this event. Thank you. Thanks, everyone. Yeah.